purpose of this video today is to help you figure out what statistical test to use and what are the different hypotheses that we'll be covering in this course using different scenarios. I have shown you before previously this um, helping you trying to figure out the different scenarios that we will be using. And what I've said previously was you could either have one group and then your outcome is either numerical or categorical. And on that, we talked about either using the one sample Z test or one sample T test. But if your outcome is categorical, you'll use the Z test for single proportions. And then we started discussing having two groups. And again, your outcome could be numerical or categorical. And so far, we have discussed the numerical outcome, and we talked about whether your groups are paired, dependent groups, or independent. And the two tests that we covered so far were the paired t-test and the independent t-test. So what I'm doing in this video is I'm going to offer like a guide over all the different statistical tests we're using and all the different hypotheses we'll be testing. So the first thing I want you to remember is that if you want to know what is the statistical test and what is the type of hypothesis you will be testing, remember the three questions to ask. How many groups do I have? Are the members in each group related? Yani, are they paired? Are they the same people, for example? Obviously, if you have only one group, then question number 2 does not apply. And then you ask your question about your outcome. Is it a numerical outcome or a categorical outcome? Therefore, are you going to look at mu or pi? Okay, so let's look at these scenarios one by one. All right, so what if the first thing we had was if you had one group, and the first scenario is testing a hypothesis mu equal a certain value. So you had one group, and your outcome is numerical, okay? So the example I have here, a research question could be of the form, is there evidence that patients on statin have an elevated creatinine clearance level, knowing that the normal level is 6.2, you could be provided with sigma or not. If you read this question, you realize that you're only dealing with one group of people. These are the patients on statin. And what you're interested in is their creatinine clearance level, which is a numerical outcome. And you want to know if it's elevated, different than the normal level. And therefore, the normal level, which is 6.2, is obviously your mu. And therefore, the hypothesis you will be testing is mu equals 6.2. The alternative hypothesis is mu not equal to 6.2. So this is the first scenario that we have started with when we're testing the hypothesis. And the two tests we discussed was either the Z test. Sorry, let me just fix that a little bit. So we're dealing with either the Z test. No, I just keep doing that. Let me fix that again. Okay, so you're either going to be using the Z test, and you remember the formula of that Z test. That was x bar minus mu, and it's divided by sigma over root square of n. Or you were going to use what we now call the one sample t-test, and that's the x bar minus mu, and it's divided by s this time over root square of n. And your decision on whether you're going to use this one or that one depends on whether sigma is known or sigma is unknown. And we said the degrees of freedom for this test is n minus 1. And we also said that for this to work, the sampling distribution of the mean had to be normal, and that can happen either under two conditions. Either the original variable of interest, x, had a normal distribution, or n is greater than or equal to 25, so that the central limit theorem applies. Okay, so let's go back to our scenarios. So that concludes scenario number 1. Okay, scenario number 2, that's where you're interested in testing if pi is equal to a certain value and a proportion in the population. Again, how many groups is you have only one group, and the outcome variable is categorical. The example of the research question could be is there evidence that the proportion, now proportion, of spontaneous abortion is higher than the normal among refugee women, knowing that the normal proportion is 15%. So again, you're only looking at one sample, that is a refugee woman. Your outcome is spontaneous abortion, and you want to know if the rate, the proportion, the percentage is different from the normal. And the normal is what you're provided, that is the 15%. And therefore, you test the hypothesis using pi equals 0.15. The alternative hypothesis, pi is not equal to 0.15. And what test do we use? Again, here we have covered, this is the z-test, and we call this the z-test for single proportion, where it's p, which is the proportion in the sample, minus pi, which is the proportion in the population provided by the null hypothesis, divided by the standard error of proportion, which is pi, into 1 minus pi, and everything is divided by n. Okay, and for this to work, the sampling distribution of the proportion had to be normal, and the condition for that is n into pi into 1 minus pi had to be greater than or equal to 5. Okay, that was the condition. Now, as a note, when we were doing the confidence interval, we were not provided with the pi, and therefore we had to replace the pi with the p. But the correct condition is n into pi into 1 minus pi had to be greater than or equal to 5. And again, this test is called the z-test for single proportion. Okay, so let's continue with the scenarios. Okay, so now we have two groups, and I have that into two parts. The first part is when your outcome is numerical, and the second part when your outcome is categorical. Okay, so scenario number 3, the hypothesis you'll be testing is mu1 equal mu2, or mu of differences is equal to 0. So you have two groups. Members in the two groups are paired or dependent, or they are the same people. And your outcome of interest is numerical. Okay, so example of a research question: is there evidence that the mean cholesterol changes after 2 weeks on keto diet? Okay, so if you think about it, you have a group of people, you measure them twice. One before they started the keto diet, and the second time after they did their keto diet. And therefore you have two groups, but these are the same people. And therefore your null hypothesis is mu of differences in cholesterol is equal to 0. There's no change. Or you can write it as mu of cholesterol level before equal mu of cholesterol level after. Remember, always, the null hypothesis stays no difference, no change, nothing is happening, there's no departure from the state of nature. Whereas the alternative hypothesis is the complement of that. It's everything else but this, and therefore it's mu of difference different than 0, or mu of before not different than mu of after. It's not equal to mu of after. Okay? And quickly here, let me help you a little bit mention a few things. We talk about the dependent variable and the independent variable. Your dependent variable is your outcome. Your outcome here is cholesterol level. And your independent variable, this is your grouping variable. This is your exposure. And your exposure is whether they were exposed to the keto or not exposed to the keto. So your independent variable is before the exposure and after the exposure. And therefore, you have two groups. Now, let's go to the test we use in this scenario. The test we used in that scenario was the pair t-test, which had the following form: d bar over the standard deviation of the differences, and it's divided by square root of n, and the degrees of freedom was n minus 1. And for the requirement for this to work was either the differences had a normal distribution, or the number of pairs was greater than or equal to 25, so that the central limit theorem applies. Okay, let's move along. The fourth scenario is, again, you have mu of group 1 equal of mu of group 2. That's the null hypothesis. You have two groups. Members in the two groups are independent, therefore they're not the same people, therefore you cannot calculate differences. And again, the outcome variable is numerical. You're interested in numerical outcome, therefore you're looking at mu. Example of a research question: are people on medication Z for 2 weeks have different mean depression score than people on placebo? Okay, so who are the two groups? Well, one group is receiving the medication. The second group is not receiving the medication, they're receiving a placebo. And therefore, the null hypothesis is going to state that the mu of depression score is the same between the two groups. The alternative hypothesis, the two mu's are different. And the outcome here is depression score. We call this the dependent variable. And the exposure here is whether they're receiving medication Z or placebo. And we call this the independent variable. The test we use here is the independent t-test, and it has the following form. It's x bar 1 minus x bar 2, and you divide by the S pooled, and we had talked about what is the S pooled, and the square root of 1 over n1 plus 1 over n2, and we said that the degrees of freedom of that S pooled is the degrees of freedom of the t-test, and therefore it's n1 plus n2 minus 2. Now, for this to work, I have given you a very stringent requirement, which that the degrees of freedom had to be greater than or equal to 25. Also, we're making an assumption here to be able to calculate this S pooled that both S1 and S2 are estimating the same sigma, yani sigma 1 is equal to sigma 2 equal to the same sigma. That is the assumption we made so that we were able to pool S1 and S2 together to get the S pooled. And remember, I told you S pooled is some sort of an average, but it's a weighted average. You just cannot add S1 to S2 and divide it by 2. It won't work. Okay, so let's continue. All right, so now we're into the two groups. We're still with the two groups, but the outcome this time is going to be categorical. And therefore, the null hypothesis is pi in group 1, and proportion in the population of group 1 is equal to the proportion in group 2. But since you're using the same people, another way to write it, though we're not going to use it a whole lot, but I just want to mention this, is that you can write it as the proportion of those that change from yes to no is equal to the proportion of those that change from no to yes. And the proportion of those two that move from one side to the other side is the same as those that move from the second side to the first side. And when I'm talking about sides here, I'm not talking about group 1 and group 2. No, I'm talking about the outcome. So your outcome is, if your outcome is yes or no, those that change from no to yes is the same as a proportion than those to move from yes to no. If your outcome is not yes, no, it's pass and fail, then the proportion of those that passed from pass to fail is the same as those that passed from fail to pass. Okay. Now, if you find it difficult to write the null hypothesis this way, it's perfectly fine to write it that way. So how many groups we have? We have two groups. Members in the two groups are paired. Ganeta, the groups are dependent. You can think about it as if it's the same people in every group, for example. And the outcome here is categorical. Here's an example. Is there evidence that the proportion of students satisfied with advising process changes after adoption of a new procedures? So what we did here is we get a group of students and we asked them if they were satisfied with the advising. And then we introduce a change in the advising process, so maybe like the next semester, and we get the same people. It's very important here to get the same students. And after they went through the new advising procedure, you ask them, are you satisfied or not? So you write the null hypothesis, pi of 1 equal pi of 2, where 1 is before the introduction, so it's proportion satisfied with advising before the new procedure. 2 is the proportion satisfied after the adoption of the new procedures. Obviously, the alternative hypothesis, these two proportions are different. The outcome is satisfaction with advising. This is your dependent variable. And the exposure is before and after the application of the new procedure. This is your independent variable. And here the test that we're going to use, I'm not going to go over the formula, but just quickly, is the test here is called a chi-square. It's a chi-square. And chi is represented with something that looks like an x, but it's not an x, it's squared. Now this specific chi-square is called the McNemar chi-square. Okay, So this is the McNemar chi-square. And it has degrees of freedom, and it has also requirements that you need to meet to be able to use it. Otherwise, you cannot use it. مثل dependent t-test in the Z. It also has requirements. So it's a chi-square. It's the McNemar chi-square. It has degrees of freedom, and it has requirements. And we're going to cover that in coming lectures. Okay, scenario number 6. Still, you're interested in comparing two groups. But this time, members in the two groups are unpaired. They're independent. These are different people, for example. Still, the outcome is categorical, and the null hypothesis is the same. Proportion in group 1 is equal to proportion in group 2. Okay, remember, we write it using the population parameters. So, example of a research question: is there evidence that the proportion of people contracting corona among men is different among women? So, think about your two groups. Meaning your two groups, well, men and women. And what is your outcome of interest? Well, whether they contracted corona. Are they the same people in the first group or not in the second group? Obviously, they're not, so it's unpaired. There is a way that you can do it paired if you get like spouses or brothers and sisters. But for this course, we're going to keep it simple. For this course, we're only going to consider they're paired if we're using the same individuals. So your null hypothesis is going to be the proportion contracting coronavirus in men is equal to the proportion of contracting coronavirus in women. The alternative hypothesis, these two proportions are different. Again, your outcome is contracting coronavirus, and this is your dependent variable. Your exposure is gender, and it's your independent variable. So what test do we use here? Well, it's still a chi-square. So it's still a chi-square, right, the same way, but this time it's not the McNemar chi-square. This is going to be the Pearson chi-square, okay? The Pearson chi-square. So it's still a chi-square, meaning that it has a different formula, but once you calculate that chi-square with its degrees of freedom, you'll go to the chi-square table, and from that table you will be able to get the p-value. So once you calculated your chi-square, whether it's a McNemar chi-square or a Pearson chi-square, once you figured the value, you go to the table to get the p-value. Like the t-test. Remember, we have done the one sample t-test, the paired t-test, independent t-test. Each one of these have a different formula. But once you calculate a t-test and you know the degrees of freedom, you go to the same table to get the p-value. Similarly with the Z, you have a Z for one group and you have a Z for single proportions. So once you calculate the Z, even though they have different formula, you go to the same Z table to get the p-value. Okay, so again, it's a chi-square. It has degrees of freedom and it has a requirement which we will discuss once we'll talk about the Pearson chi-square. Okay, so that concludes the two groups. What happens if you have three or more groups? Again, you have the two possibilities based on your outcome. So part one, your outcome is numerical. So here you're testing a hypothesis where mu of group 1 is equal to mu of group 2 is equal to, I don't know how many groups you have, as long as you have more than 2. So we say all the way up to mu of group k. Now notice the alternative hypothesis here. We do not say that mu of group 1 is different than group 2 is different because that will not cover all the possibilities. Remember, the alternative hypothesis is the complement of the null hypothesis. It covers all the other possibilities. And therefore, the way to cover all the other possibilities is to say at least one of the mu's is different from the other. Because all of the mu's could be the same except for the first one. And you would be rejecting the null hypothesis. So how many groups do we have? We have k groups, as long as k is greater than 2. Members in the k groups are paired. They're dependent. They're the same people. And the outcome variable is numerical. An example of that question: is there evidence that the mean grades for the same students is different for math, biology, chemistry, and statistics? So how many groups do I have? Well, I have the math group, the biology group, the chemistry group, and the statistic groups. These are 4. My outcome is their grades, which is numerical, so I'm going to look at their averages. But since I'm looking at the same students, then I have to take that into account. So I write my null hypothesis: mu grade for math equal mu grade of biology equal mu grade of chemistry equal mu grade of statistics. My alternative hypothesis: at least one of the mu's is different. So maybe students could be having the same grades in math, biology, and chemistry, but in statistics is different. Or maybe chemistry and statistics are different from math and biology. So at least one of them is different is enough to reject the null hypothesis. The outcome variable is grade, which is your dependent variable. Your exposure variable is course, which course we're looking at, and this is your independent variable. Now, in this scenario, what test do we use? Again, I'm going to mention the test, but I'm not going to go over the formula. Here we're going to use a test that is called the ANOVA test. And ANOVA, um, actually, it's the ANOVA analysis for the F test. So ANOVA is an acronym where N-O-VA. And AN stands for analysis, O for of, and VA for variance. So it's the analysis of variance. Okay? And that's why some books they call it the AOV. It's exactly the same thing. ANOVA, AOV, analysis of variance is the same thing. But since these are the same people, you're going to account for blocks in this analysis. Blocks is like pairs, but since it's more than two, we have to talk about blocks. And once you do your calculation correctly, you get an F test, which has also degrees of freedom. Actually, it has 2 degrees of freedom. And you go to your F table, and from that, you can get your p-value. Okay? And again, it has some requirements that we will also discuss when we get there. Okay? All right, so let's move along. Scenario number 8, still the same setup. You have K groups. So you write your null hypothesis the same way, the alternative hypothesis the same way. But here the members in the groups are unpaired, they are independent, these are not the same people. Again, as an example, your outcome is still numerical. So an example is there evidence that the mean length of stay for surgery patient is different between the Ministry of Health, the private insurance, and the out-of-pocket patients. So I have 3 types of patients that underwent surgery. Those where the Ministry of Health are paying for the cost, those that the private insurance pays for the cost, and those that pay out of pocket. And I want to know if the average length of stay between these 3 groups is the same or different. Maybe, maybe some hospitals prefer to keep those that are paying out of private insurance longer to overcharge them, for example. So you write your null hypothesis mu of the first group, Ministry of Health, is equal to mu length of stay. Remember, this is mu of length of stay. For private insurance, equal mu of out of pocket. Your alternative hypothesis is going to be at least one of the mu is different. So maybe only the private insurance stay longer, whereas the Ministry of Health and out-of-pocket stay the same period, for example. It's enough to one of the mu's to be different to reject the null hypothesis. What is your outcome variable? It's the length of stay. Again, this is called your dependent variable. What is your exposure variable? Well, it's the type of patients, Ministry of Health, private insurance, out-of-pocket. And this is called your independent variable. So in this scenario, what type of test do we use? Well, it's still the ANOVA test. It's still the ANOVA test, analysis of variance. But in this scenario, we do not have blocks. Okay? You set it up exactly the same, whether you had blocks or no blocks. You set it up to calculate your F test. It's just the way you set it is a bit different. But once you get your F test, which has degrees of freedom, you go to your F table, and from your F table, you get a p-value, and everything is the same. Remember, if your p-value is larger than alpha, you fail to reject. If it's less than alpha, you reject. Okay? All right, so let's move along with our scenario. So that was scenario number 8. Now we're still with 3 or more groups, but now your outcome is going to be categorical. Again, pi group of group 1 is equal pi of group 2 is equal all the way up to pi of group k. I don't know how many groups you have. You could have 3, 4, 5, 6, 7. And the alternative hypothesis is set the same way. At least one of the pi is different. So you have k groups, as long as k is greater than 2. Members in the k groups are paired. They're dependent, so they like the same people. And the outcome variable is categorical. An example of that, well, is there evidence that the proportion of people liking the taste of the following yogurt flavor, plain, strawberry, or vanilla, is the same? but we're using the same people. So maybe like you're running a test and you got 10 volunteers and you had them try the plain yogurt, the strawberry yogurt, and the vanilla yogurt, and you ask them every time if they liked it or not. And you're interested, is there a difference in the proportion of people liking each of the tastes? So the null hypothesis is going to be pi liking the plain yogurt equal pi liking the strawberry yogurt equal pi liking the vanilla yogurt. The alternative hypothesis, at least one of the pi is different. Your outcome variable is whether they liked it or not, yes or no, since this is your dependent variable, and your exposure are the different variables, and this is your independent variables, where you had, here in this example, you had three groups, three flavors. So what test do we use in this instance? Let's go back to our board here. Well, it turns out that again, since you're dealing with categorical, you're going to again use a chi-square. So we're back to the chi-square. But that chi-square has a very specific name, and it's called the Cochrane Q chi-square. And it also has degrees of freedom, and it also has requirements. But once you calculate it, you go to your regular chi-square table to get the p-value. But I'm going to say something is that this Cochrane Q is a bit computationally difficult to do, so we're not going to actually calculate Cochrane Q in this class. It's hard to do that. And let's go to the final scenario. So the final scenario is when, again, you have different groups. You're interested in proportions. But here the groups, the members of the groups are unpaired independent. So example of that is there evidence that the proportions of side effects is different among patients taking drug A, drug B, drug C, and drug D. So you have four groups. You have different people in every drug, and you're looking at the proportion of side effects. So proportion of side effects in drug A equal proportion of side effects drug B equal proportion of side effects in drug C equal proportion of side effects in drug D. This is your null hypothesis. Your alternative hypothesis, at least one of the proportion is different. Your outcome variable is side effects, yes or no, categorical. And your exposure variable, your independent variable, is the drugs. Okay? So which test do we use? Well, again, it's a chi-square. But the good news here is this is the chi-square that we covered when you had two groups. So whether it's two or more groups, it's the same chi-square. This is the Pearson chi-square. And the way you calculate it is the same. So once we cover the Pearson chi-square for two groups, you know how to do it for 3, 4, 5, 6 groups. It has degrees of freedom and it has requirements. And once you do the calculation, you go to your chi-square table and you get your p-value. And if your p-value is larger than alpha, you fail to reject. If it's less than alpha, you reject. Everything else is the same. Okay? So this way, we have covered all the scenarios we're going to talk about in this course, all the different type of questions, all the different types of testing hypotheses that we will do in this course. One last word I want to mention is that you heard me talk about the independent and dependent variable. By now, the dependent variable is clear. It's your outcome. Your independent variable is your exposure, but this is actually your grouping. How many groups do you have? That is your independent variable. Okay, so the last thing I had for you is a set of questions, an example, and I want you to get out of these examples to find the null hypothesis, to write the null hypothesis and the alternative hypothesis, to identify the dependent and independent variable, and to specify which test we should use. Okay, so question number one. Question number one says, a researcher compared the proportion of patients complying to their medical treatment among two groups, those followed by phone calls and those not followed by phone calls. So how do you figure out which test to be used? Remember the three questions. How many groups? Are they the same people, or are they the members matched and paired? And what's your outcome? So how many groups do I have? Now here it's very obvious. It's easy. It's the question itself says that we have two groups, those that were followed and those that were not followed. And the outcome is whether they were complying or not. So that's a categorical outcome. And there's nothing that says that there is any kind of matching between these two groups. So these are independent groups. If you go to your map, so two groups, Your outcome is categorical. They're independent. You're going to use the Pearson chi-square. Now, in the Pearson chi-square, how do you set up the null hypothesis? You're going to say that the proportion of complying with medication in those followed by phone is equal to the proportion of patients complying to their medical not followed. The alternative hypothesis, these two are not the same. Your dependent variable, this is your outcome, complying to their medical treatment, and your independent is whether they were followed or not followed. Okay? Question number 2. Is there evidence that the average hours of sleep among patients taking clarinase is different from the normal average, which is 8 hours? How many groups do we have? Well, it seems that we only have one group, those that are taking clarinase. We don't have any other group. And where's our outcome of interest? Well, this is a number of hours of sleep. And therefore, the test that we will be using is, if you want, let's go back to the map. So if you have only one group and your outcome is numerical, so you're either going to use the one sample Z test or the one sample T test, depending upon if you have sigma or you do not have sigma. Okay? So your null hypothesis is going to be mu of hours of sleep for patients on clarinase equal to 8 hours. Remember, the null hypothesis, there's no departure from the state of nature. And the state of nature is that it's 8 hours. Your alternative hypothesis, this mu is not equal to 8 hours. And your dependent variable is the hours of sleep. Your independent variable here is, well, it's not like you have two groups, you only have one group. But if you were to pick, it would be taking clarinase. You don't have those that are not taking, but you get the point. Okay. Question number 3. Is there evidence that number of words typed per minute increases after receiving hypnosis therapy? Let me correct this, per minute. In this study, the researcher is going to ask a group of volunteers to type a paragraph. He will time them, then he will have them go through a hypnosis therapy, and then ask them to type a similar paragraph and time them again. So what is happening here? We have a group of people, but they're measured twice, before the hypnosis and after the hypnosis. And therefore, we have two groups, before and after. These are the same people, so it's paired. And the outcome is their speed, the number of words typed per minute. So the outcome is numerical. So what test do we use? Let's go back to the map. The map says that if you have two groups, your outcome is numerical, but these are the same people. You're going to use the paired t-test. The null hypothesis is going to be the mu of average mu of words typed per minute before hypnosis equal mu of words typed after hypnosis. These two are the same. Or you can write that the mu of the differences in words typed per minute is equal to 0, and there is no change. The alternative hypothesis, these mu are different. Your outcome variable, your outcome yani dependent variable, is the number of words typed per minute. Your independent variable, yani your exposure variable, is receiving hypnosis. So before receiving and after receiving the hypnosis therapy. Question number 4. The rate of COVID-19 complication is 20%. This is a worldwide observation. A researcher wanted to know if the proportion of complication is different among the Lebanese population that contracted the virus. He collected data on the COVID-19 cases in Lebanon and determined the rate of complication among them. Okay, so how many groups do we have? Well, he only looked at one group. This is the Lebanese population contracting the virus. And within that group, he calculated the rate, the percentage of complications. And he wants to compare that proportion to the well-known worldwide, which is 20%. So I hope that it's clear to you that this 20%, this is the pi that you will be testing. So your null hypothesis is going to be pi of complication for COVID-19 is 20% among Lebanese population, because the null hypothesis states that there's no departure from the nature. Yani the Lebanese population are not different from any other population. So the null hypothesis is going to say the proportion of complications for a Lebanese population contracting the virus is 20%. So what test do we use? Again, we have one group. Your outcome is categorical. You're going to use the Z for single proportion. So what is your outcome variable? Complication is your outcome variable. It's either present or absent. This is your dependent variable. Your independent variable, your exposure variable, where here you have it, but you don't have those that, and there's no variability in it. So it's Lebanese population. So Lebanese population is your exposure, but it's only one group. Okay, question number 5. During an election, a poll looked at 1,000 people and asked them if they planned to vote. Then 4 weeks afterwards, they contacted the same people and asked them again if they planned to vote. The researcher was interested in whether the proportion of those planning to vote changed over the past 4 weeks. All right, so we have the same people. They were measured twice, before and after. And the measurement was whether they planned to vote or not. So the measurement was on a categorical outcome. So how many groups do we have? We have two groups. I mean, it's the same people, but it's two groups, before and after. So it's like at time 0 and at time 4 weeks. And the outcome is whether they want to vote or not. So let's look at our map, two groups. The outcome is categorical, but these are the same people. So it's going to be the McNamara chi-square. What is the null hypothesis? Proportion that plan to vote at time 0 equal proportion of those that plan to vote at 4 weeks. That's the easiest way. You can write it differently. You can write it the proportion of those that changed their planning from not to vote is equal to the proportion of those that changed from planning to vote to not planning to vote. I know it's a bit complicated the second way, so if you want to stick to the first way, is fine. Proportion of those planning to vote at time 1 is equal to the proportion of those that planning to vote after 4 weeks. All right, question number 6. A study randomly put 3,000 postmenopausal women into 4 groups. Group 1 received placebo, Group 2 received a special diet, Group 3 received progesterone, and Group 4 received estrogen. The study followed these women for 10 years and looked at the occurrence of heart disease. So how many groups do we have? Well, obviously we have 4 groups. And are they the same women in every group? No, they're not. These women are different women. What is the outcome of interest? Well, heart disease, occurrence of heart disease. This is yes or no, whether they developed heart disease or not. So you have 4 groups, independent, and your outcome is categorical. Let's look at our map. What does our map say? So you have 3 or more groups. Your outcome is categorical. These are independent. So you're going to use, again, the Pearson chi-square. So how do you write your null hypothesis? Proportion of heart disease in group receiving placebo equal proportion of heart disease in group receiving special diet equal proportion of heart disease in those receiving progesterone equal proportion of heart disease in group receiving estrogen. Now, for this to be complete, I have to say that this is for postmenopausal women. The alternative hypothesis, at least one of the groups have a different proportion of heart disease, or at least one of the proportion of the heart disease is different between these 4 groups. Your outcome variable, your dependent variable is the occurrence of the disease. Your independent variable, your exposure variable is the 4 grouping that we talked about. See, again, remember, your independent variable, your exposure variable is your grouping variable. All right, question number 7. A study looking at the effect of a new herbal drug on GERD randomly put, GERD is a disease like it's an acid reflux disease, randomly put 100 patients suffering from GERD into 2 groups. The 50 patients in group 1 received the new herbal drug, while the other 50 patients in group 2 received the placebo. At the beginning of the study, the researcher wanted to be sure that the level of GERD is the same between the 2 groups, and therefore they administered a measuring tool called the GERD Q. Sorry, I forgot a D here. So it's the GERD Q, yielding a score from 7 to 32. The higher the score, yani, the more severe the GERD symptomology is. The average of the GERD Q between the 2 groups were compared at time 0. Okay, because that's where they want to make sure that they are similar. So what do we have here? How many groups do we have? We have 2 groups. One group received the treatment, and another group received the placebo. Okay, are they the same people? Is there some sort of a pairing or matching? No, there's no pairing, no matching. What is the outcome? Well, the outcome is the score on the GERD-Q. It's numerical. So what test do we use? Let's go to our map. We have two groups. The outcome is numerical. The groups are independent, so we're going to use the independent t-test. Okay, so how do you write your null hypothesis? Mu of GERD-Q score for those receiving the treatment at time 0 equal mu of GERD-Q score for those receiving the placebo at time 0. The alternative hypothesis, the mu's are not equal. Your outcome variable, yani your dependent variable, is the GERD-Q score. Your independent variable, yani your exposure variable, your grouping variable is whether they received the placebo or whether they received the treatment. Question number 8, and I think this is the last one. A researcher put 4 rats um, in each of the following 5 groups. So he put 4 rats in each of the following 5. These are not the same 4 rats. So you have in total 20 rats. So 4 rats in group 1 was the control. 4 rats in group 2. The group 2 was given insulin. Group 3 was exposed to gamma ray, and group 4 was given alcohol shot, and group 5 was given vitamin C. After 2 weeks of this treatment, all rats, and all 20 rats, were sacrificed. So let me write here all 20 rats so it becomes clear that these are not the same. Were sacrificed, and the livers were weighted to compare the average weight of the liver between the 5 groups. So again, our 3 questions: how many groups do we have? We have 5 groups. Are they the same rats, or is there any kind of pairing or matching? No, there's nothing. And what is our outcome variable? The weight of the liver. So what test do we use? So you have 3 or more groups. They're independent, they're not the same, and your outcome is numerical. The weight is numerical. So you're going to use the ANOVA F-test without blocking. Okay, so how do you set it up? What is your null hypothesis? You're going to write that the mu liver weight of group 1, and the control, is equal of mu of liver weight for those on insulin treatment, equal mu of liver weight on those exposed to gamma ray, equal mu of liver weight on those given alcohol shots, equal mu of liver weight for those given vitamin C. The alternative hypothesis is going to be at least one of the mu is different from the others. So, for instance, if all the groups had the same weight of liver except for vitamin C, which is different from the rest, then you still reject the null hypothesis. Okay, any departure from the null hypothesis you're going to reject. Okay, what is your outcome? What is your dependent variable? Weight of the liver. What is your exposure? What is your independent variable? What is your grouping variable? Well, it's the different exposure, whether they received nothing, or insulin, or gamma, or alcohol, or vitamin C. Okay, so that concludes this lecture. The aim of this lecture is to put things into perspective, so that you start have a feel of the different research question and hypothesis we test, and how do we determine which test do we use, how do we set up the null hypothesis and alternative hypothesis, and how do we pick which test we're supposed to be using. And I hope this helped you make things a bit clearer for you, and see you in coming videos.